All right, here we have example 3. We are given 2 of the zeros, and we want to find all of the real zeros. So this is a degree 4 problem, which means that given the fundamental theorem of algebra, which we will be learning in section 2.4, we know that degree 4 polynomials have 4 zeros. They could be repeated zeros, like 1/2 with multiplicity, so that counts as 2. They could be imaginary. This one asks us to just find real zeros, so we're not dealing with imaginary yet until section 2.5. The important thing is to remember that since it's degree 4, it's going to have 4 zeros. Okay, so if we know that 1/2 is a 0, we can do synthetic division with our polynomial. So we're going to go ahead and do that. 4, -4, -11, 12, -3. Let's go ahead and do our synthetic division. So break down the 4. 4 times 1/2 is 2. -4 plus 2 is -2. -2 times 1/2 is -1. -11 plus -1 is -12. -12 times 1/2 is -6. 12 plus -6 is 6. And 6 times 1/2 is 3. -3 plus 3 is 0. It shouldn't be surprising that we have a remainder of 0, because they basically told us that 1/2 is a 0. So if it is a 0, that means that x minus 1/2 is a factor and should divide in evenly with the remainder of 0. Now to do the second 1/2, because it's a multiplicity of 2, we want to divide it again. But this time, instead of dividing it into the original with the same result, we're going to divide the 1/2 into the polynomial we have left. I don't even need to stop and write out this polynomial. It would be a degree 3 polynomial, 4x cubed minus 2x squared minus 12x plus 6. And the 0 is the remainder, so that's not even part of our polynomial. So when we do this step with our division, we don't need to worry about the 0 at the end. That's not part of the polynomial for our division. So I'm really going to take my line to there, because that 0 doesn't matter anyway. Set that aside. Okay, so I'm going to bring down the 4, and then 4 times 1/2 is 2, and -2 plus 2 is 0, and 0 times 1/2 is 0. Add those together, ends up bringing down the -12. -12 times 1/2 is -6. And we have our last remainder of 0. So since the remainder is 0, that means our constant term is 12. You just kind of go back this way. The linear term would be 0, so I don't need to write 0x. And then our first term would be 4x squared. Now this makes sense, 4x squared minus 12, because we started with a degree 4 polynomial, we divided out a 0, we now have a degree 3 polynomial, we divided out another 0, we now have a quadratic. So far what we've got here is that our polynomial should be equal to x minus 1/2 times x minus 1/2 times 4x squared minus 12. Okay, so to find the other real zeros besides the two 1/2s, we would need to solve 4x squared minus 12. So let's go ahead and set 4x squared minus 12 equal to 0 and solve it. It is a quadratic. We can factor it, try factoring it. If we factor it, we can factor out a 4, and then we have x squared minus 3. And that doesn't really factor. There's no factors of 3 that add up to 0. It would create square roots. So instead of trying to do it that way, let's just solve this. We're missing our middle term. We don't even need to use quadratic formula. No middle term means we can move the 12 to the other side, divide both sides by 4. So x squared equals 3. And don't forget, when you put a square root into a problem to get rid of a square, you must consider that there's both a negative and a positive possibility. So that gives us x equal to positive or negative 3. Those are the other real zeros of this polynomial. So it has 4 zeros, 4 real zeros, in fact. 1/2, positive square root of 3, and negative square root of 3. Positive and negative square root of 3 are real. They're not imaginary. They happen to be irrational. They are still real answers. If wanted to, we could write out this entire polynomial now in a form that's kind of all factored, but a little bit weird looking. So just for fun, let's think about what that would look like. If we have an x minus 1/2 and an x minus 1/2, and now we know our other zeros are x minus square root of 3 and x plus square root of 3. The graph of that function would be a polynomial that has x-intercepts at 1/2, positive square root of 3, whatever that decimal is, 1.7, and negative square root of 3, so approximately negative 1.7. So that polynomial would have x-intercepts at those 3 points, and at positive 1/2, the graph would touch the x-axis because it has a multiplicity of 2. Now, if we want it to be our original problem, it has a 4. So in order to make it our original problem, 4 that we took out during this step here, we would need to also include a 4 at the beginning of our problem. That doesn't change any of our zeros. The zeros are still 1/2, 1/2, square root of 3, and negative square root of 3. All that does is change the stretch. The horizontal stretch or compression, if it was a fraction, of our polynomial. It changes where our minimums and maximums and y-intercept are, but it does not change those x-intercepts. It does not change our zeros. So that is a way that you could write this polynomial in a funky factored form. Now, if you want a factored form that doesn't quite look so funky, another thing you could do is you could take this 4 and split it into 2 2s. So you could split it into 2 times x minus 1/2 and another 2 times your x minus 1/2. You could leave this funky as like x minus square root of 3 and x plus square root of 3. Or what if we did this? 2 distributed through this would be 2x minus 1. 2 distributed through this would be 2x minus 1. And then if we go ahead and multiply these together so that we don't have those strange square roots, we'll simply have x squared minus 3. This is kind of a nice factored form. There's no fractions. There's no roots. It's all these beautiful integers just by multiplying things together to make it a little prettier. You will see polynomials given to you like this. And it's important to understand that this polynomial with the 4 in front has exactly the same x-intercepts, the same zeros as if it would have without the 4. It's only that stretch and compress and the minimums and the maximums and the y-intercept that would be different if you were to leave out the 2 times 2 and the 4 at the beginning. Okay, so let's kind of just connect this all together. Everything we're talking about here goes with what we're going to learn in section 2.4. So we've already kind of got a head start on 2.4. We learned about this in chapter 1. Suppose p is a polynomial function of degree greater than or equal to 1. The following statements are equivalent. The real number c is a 0 of p. So p of x is our polynomial function, and c is one of the zeros. That means that p of c equals 0. We know that from the factor theorem and from the remainder theorem. We know that if we divide by the 0 c using synthetic division, we get a remainder of 0. X equals c is a solution to the polynomial equation. If we needed to actually solve a polynomial equation, then the solutions would be found by finding the zeros. We will get to that in the upcoming sections. X minus c is a factor of p of x. So 0c is interchangeable with factor x minus c. Two different terminologies. We use factors to create our actual polynomials, to write them out in factor form or multiply them together to get a polynomial. But we use the zeros to tell us where those x-intercepts are, what the solutions are, etc. And then the point c comma 0 is an x-intercept of the graph of y equals p of x. So the x-intercepts are the same places where the zeros are, those are the same thing, the solutions are the same thing, and we can easily convert those zeros into factors. It all goes together, it all fits together, it's all important to understand how those fit together as we finish up the rest of chapter 2.